Okay, we just finished chapter 4, which is on probability, and we actually didn't finish the whole thing, but I think we got the important parts of probability that we'll need to carry on to inferential statistics. And so now we're going to talk about probability distributions. Now, the probability distribution section is broken up to 2 chapters. This first one, chapter 5, focuses on it focuses on this binomial probability, but it's an introduction to probability distributions, but it more discusses what they call discrete. This is an R. Discrete probabilities. So it's going to focus on discrete probability distributions. We did talk a little bit about discrete and continuous, right, at the very beginning. So it's the same situation. And so here the data that we're talking about is discrete, which means it's we're looking at whole numbers or a finite quantity of things. And so in this case, there's one example that we're going to talk about in section 5.2, and after that, the main focus of our discrete probability distributions would be on what we call binomial probability distributions. And in chapter 6, we'll talk about the other side of the distribution, which is a continuous probability distribution. And we'll introduce one really simple one, simple distribution, and then we'll introduce our big continuous distribution that we're going to study for the rest of the semester, called the standard normal distribution. Okay, so let's talk about some discrete probability distributions. But first, before we talk about probability distributions, we're going to talk about random variables. I guess 5.1, there's an overview. And here's an overview. They actually do talk about discrete probability distributions. So the probability distributions and the probability is that arrow link. Remember we talked about descriptive. Descriptive statistics and inferential statistics. And then we talked about an arrow connecting those two things, and the arrow connecting those two things are probability. Probability, and then these next 2 chapters, probability distribution, kind of makes this a seamless process between descriptive and inferential statistics. Okay, so I want to kind of highlight the last sentence over here where they talk about a probability distribution is kind of like the theoretical or the classical approach to probability. Probability distribution will describe what would probably happen instead of what actually did happen. So if we take a look at a situation and we take a look at something that did happen, that's like your relative frequency approximation to probability. You know, we tossed a coin 1,000 times, 530 times it came up heads. So that's what actually happened. The probability distribution describes what should happen, and that is what should happen when we toss the coin 1,000 times is that we should get 500 times it should be heads, 500 times it should be tails. Okay? And so what we're going to do is we're going to take a look at what probably should happen based on our probability distributions, and then we'll compare that to what actually did happen. And that's how we'll assess our situation, and that's how we'll apply our inferential statistics when we get there. Okay? So probability distributions, what we have is that we'll know all the information based on probability, and then we'll use that information to make inferences. All right. So I've been giving that example about tossing a coin 1,000 times, and here's their example where they roll a die. I think rolling a die gives a little bit more variety because it's 1 out of 6. So if we say roll a die, how many times did they roll this? I don't know, whatever this F adds up to be. So if we roll a die this many times, what we have is our relative frequency approximation for probability. That's what this is. So let's label that. So let's call this relative frequency approximation for our probability. And then what we have here is our classical, or they call it classical, right? That's what we call it. Classical probability. And so what we do is we compare our classical probability with the relative frequency probability, and then they should be close to being the same. So I'm kind of saying the same thing I said earlier, except this time we're talking about rolling a die instead of tossing a coin. One thing I do want you to notice on this page is this idea that whenever we're doing an experiment ourselves and we're collecting data, we're talking about a sample, and we're talking about statistics for a sample. And so if you notice the mean and standard deviation here, it's based on the sample. That's X bar and S. And then when we're talking about our classic probability, the probability that we get is assuming that this is what we would expect for the whole population. And so we use the population parameters as the symbols, the mean and standard deviation as mu and sigma. And so I think in the calculators I did mention 99% of the time when we look for standard deviation, you're always going to look for SX in your calculator. And that very little time when you'd be looking for the standard deviation is the population standard deviation. That's when you come up with, that's when we do a theoretical probability on a probability distribution problem, and then that's when we're going to come up with sigma. Okay, and we'll see an example of that later on. Okay, definition, random variable. So the first page of my exam, you know what the first question is on the test, right? What's the first question on my test? Definition of statistics. So I do like definitions just so you kind of are able to formalize some ideas and thoughts into words in English and be able to explain things. And so I remember having this in one of my exams. I don't know if it was a midterm or a final, but I asked people to define a random variable. So random variable, just reading it is kind of weird. A random variable is a variable typically represented by X that has a single numerical value determined by chance for each outcome of a procedure. What? So a random variable is a numerical value, and associated with this numerical value is some sort of probability. So determined by chance means a random variable should have a corresponding probability. Let me write that out. So this isn't exactly a definition. If I were to ask you for the definition, I'd rather see what's up here already, but I'm going to append to this. A random variable has a corresponding probability. So we might, if for a discrete random variable, we'll have a finite number of random variables. So each of those numbers in the random variable would have an associated probability to it. Okay, and then so putting the random variable and these probabilities together would give you the actual probability distribution. So probability distribution, some sort of description that gives the probability for each random variable. So there's usually 3 formats to represent a random variable, and you can see it from a graphical point of view, you can see it from a numerical point of view with a table, or you can see it with a symbolic point of view with a formula. So for the most part, we're going to rely on, for discrete distributions, we'll rely on a table because we're looking at a finite number of things. For a continuous distribution, it'll be too hard to look at a table because you have an infinite number of values. So we're not going to look at a table for a continuous probability distribution. For that, we'll look at a graph. Now, the 2 main distributions that we're going to consider are the binomial distribution and the normal distribution. Both of those have their own formulas, but the formulas are complicated. And so we can take a peek at the formula, but we won't really use that formula. We're going to rely more on tables and graphs, and then we're also going to rely on our calculator commands to help us find the values that we need to find. Okay, so that's a random variable, and that's a probability distribution. So this is where they make the distinction between discrete and continuous. A discrete random variable is either a finite number of values or a countable number of values. Mathematically, the whole idea about a countable number of values is valid because you can keep counting all the way off to infinity, but just for our sake, we can just assume that we have a finite number of values just to make things easier. And then a continuous random variable has an infinitely many values between any interval that you look at. And so, like I mentioned, the best way to describe a continuous random variable is not with a table, because a table gives you a list of number of things. Instead, the best way to describe a continuous random variable is with a graph. And the graph has a special name, and we'll see that name in Chapter 6. Okay? All right. So, here's an example. This is a probability distribution that is described by a graph. Basically, it looks like a histogram, and more precisely, because we're taking a look at relative frequencies out of 100%, and we'll talk about this idea that it comes from 100%. We can look at this as if it was a relative frequency histogram. So this is an example. I can't tell exactly how they got this graph, but we can come up with our own stuff in our calculators. So we're talking about discrete, the requirements for probability distribution, and maybe I'll put in parentheses here discrete probability distribution. And because we're talking about a discrete probability distribution, we could take a look at these probabilities. By the way, another example of representing a probability distribution aside from a graph is a table, right? So usually you would have a table that has an X on one side and then the probability on the other side, and then you can have numbers here, 0, 1, 2, 3, and then you can have probabilities here. And remember, our probability should be between 0 and 1. So each of these px's, 0.1, 0.2, 0.3, I'm going to go one more, 0.5. Nope, that's too much. Sorry. One plus 2 plus 3 plus 4. Oh, this is it. Okay, so why did I stop there? I was going to put 0.5 in the bottom of that, but why can't I put 0.5 in the bottom of that? Because it'll be bigger than 1. So one of the first properties that we have here for a probability distribution is that when you add up all these probabilities, they should all equal to 1, exactly 1. It can't be less than 1, can't be more than 1, it has to be exactly 1. So these probabilities added up together should be exactly equal to 1. And then the second one is saying that each of these probabilities have to be between 0 and 1. And that is consistent with our definition of probability. We said last time that the probability has to be a number between 0 and 1. If it's a negative, that doesn't make sense as a probability. If it's bigger than 1, it doesn't make sense as a probability. So this is consistent with all we've been talking about with probabilities. Okay, so I think you have a few problems in the homework that ask you whether something is a probability distribution, and this is one way to check. You just have to make sure that all these things add up to 1, and every single one of these numbers in your P of X column is between 0 and 1. So those two things are satisfied, then we can say we have a probability distribution. Michael?
I noticed on the homework that they're like identifying words to count as discrete or continuous variable.
Yeah.
Like for example, for discrete it said number, but for like continuous it said like distance, amount, or time, or weight.
Yeah.
The other ones.
Distance, amount, time, or weight. Hard to think about these things aside from just saying yes or no to actual examples. But what I can say is that if it's something that you can count, like number of people in the room or number of boys versus number of girls, if it's something that you can count like that and it has to be a whole number, then it's discrete. And anything else would have a good chance of being continuous. Okay. All right. So, given a probability distribution, there are ways for us to find the mean of the distribution, the standard deviation, and the variance. Now, these are formulas that you can write down, and sure, you can write it down on your sheet of notes, but I don't know if I'll ask you for the formula directly, and I definitely won't expect you to use the formula unless you're comfortable with it. That's fine. But you know, if you're looking at the standard deviation here, I wouldn't even want to mess with that. And the fact is that technology can find these things for you, and so that's what we'll do. Is that we'll rely on technology. I think finding the mean isn't so bad using the formula by hand, but then when you get the standard deviation, that's a waste of time. So we'll come up with an example, and then we'll see how the mean works out, and then how for you how to find the standard deviation and variance using the calculators. And notice the difference if you look at the variance parentheses shortcut. If you look at that and you look at the standard deviation, the difference is a square root, right? So we know that to be the difference between our standard deviation and our variance. Notice also the symbols that they use. These are parameters. These are population parameters because these are representative of the population that we're finding, and these are what we would expect to be the mean, the variance, and the standard deviation for our population based on our theoretical or classical approach to probability. Okay. You could write it down, and you guys have 2 pages, you know, back and front on your 1 page back and front on your sheet of notes. You might as well write it down. I can't remember if I asked for a specific formula there, but if anything, the mean is important. Okay, so round-off rule is the same round-off rule for the statistics that we've talked about, just 1 decimal place past the original data set that you have. Yeah.
If our answer is like a decimal on the information, tell us how many
No.
We'd never know how many.
Well, the general rule of thumb is that if you're looking for a mean, standard deviation, or variance, it's like 1 decimal place past the original data. And if it's a probability, the round-off rule for probability is supposed to be 3 decimal places, but I like 4. So I'll take 3 decimal places. But I don't think I don't remember specifying how many decimal places in the test.
3 just to be safe for everything.
4 just to be safe for everything.
If we're off by like rounding up a little bit, would be wrong.
It depends. Okay. Now, this sometimes we use this idea of a range rule of thumb, and it's going back to the idea of usual and unusual values again. And so it's the same kind of theme. Our usual values would be within 2 standard deviations from the mean, and our unusual values is past that. And so we get, I'll draw the same picture here, but it's the same picture that we've seen all along. We can have the mean here in the middle, and this is mu plus sigma, and this is mu plus 2 sigma, and going on the other side is mu minus sigma, and then mu minus 2 sigma. So everything in here would be considered usual. That's what they mean by maximum usual value, minimum usual value. It's just you multiply a standard deviation by 2, and then you add it and subtract it from the mean, and then that's your range of values. And everything outside of that would be unusual. So yeah, we've mentioned this idea already a bunch of times, so just try to remember 2 standard deviations from the mean. 2 standard deviations from the mean. 2 standard deviations from the mean. So that's going to be your marker for usual or unusual values. Okay, I probably should have had the example before this, but well, I think the example is next, hopefully. Kind of getting anxious to do an example. It's still not an example. Okay, we good? I'm kind of waiting for you guys to copy this, but really I should just fly through, right? Because you guys should always be able to get this. All right. All right, rare event rule, again, this is something that that will play into our inferential statistics business. So it says here, if under a given assumption, such as an assumption that the coin is fair, so we're assuming that we have a fair coin, probability of a particular observed event, say you toss a coin 1,000 times, if you toss a coin 1,000 times and then it comes up heads 992 times, which means we got tails 8 times out of this, then we have to conclude that there's probably something that's not right, that's not going on here in the assumptions. Okay? You know, there's people who practice tossing coins so that they can make it come up to whatever they want. I've done that for a little, but I got as close to like having 75% heads after tossing it a bunch of times. But you know, it's the way you hold the coin, you toss the coin. So there is a way that you can make this not fair, or there's a way where somebody that's observing you is thinking that this is a fair coin and this is a fair tossing game. But if you went home and practiced how to toss a coin and make it come up heads most of the time, then you'll come up with something like this, where out of 1,000 tosses, it's 992 times coming up heads. Then something must be going on there. Okay, if it was like 530 times it came up heads, then it's not a big deal. That's close enough. That's 0.35. That's almost a half. But 99.2, that's a lot. So unusually high, if X, the number of successes among the trials is unusually high, then we can tell that there must be something going on here. There's something going on, and so we can make our assumptions happen. So I was looking at that example. I think that example of the babies coming up with more girls than boys. You haven't heard of that, huh? Yeah, but before I told you, you haven't heard of it. I still don't know if it's real. I should look it up. Okay, and they talk about 0.5 and 0.05 as being the markers because 2 standard deviations from the mean. If you remember the empirical rule that 95% of the data is within 2 standard deviations from the mean. So 5% on the outside is unusually high or unusually low. So that's why they use 0.05 here as a marker. All right. Again, that stuff will come up later on. Here's another definition for discrete probability distributions is the expected value. Expected value of a discrete random variable is given by this formula. Now, if you're looking at this formula and saying, hey, that formula looks familiar, what is it? It's the mean. So the expected value is just, in the case of probability distributions, expected value is the same as the mean. It's just the mean. Same formula, and you can just say mean or expected value. But expected value sounds a little bit more, or a little bit less formal, a little bit less jargony. And what they're saying here is that, you know, if I roll a die so many times, my expected value should be whatever. And so that's the expected value. That's why it's called expected value. Okay, yeah, so it's the same thing as a mean. All right, finally, we're going to get to an example. And this example is an example that I found in the textbook, which is similar to, I think, one of the homework examples. And in the practice exam, the example I have that's kind of like this is a playing roulette, I think it's, or playing craps or something. But here, I think I want to do this on a separate sheet so I can cut and paste. Cut and paste some calculator screenshots. All right, so I got this from your book. So it says that there's a 99.86 probability that a randomly selected 30-year-old male lives through the year based on some data. And a life insurance company charges $161 for insuring the male to live through that whole year. If the male does not survive, then the policy pays $100,000 as a death benefit to the beneficiary. Sounds a little grim, but this is a job of an actuary. Have you heard of actuaries? An insurance company, they hire mathematicians, and these actuaries figure out probabilities and things like that. And then they figure out rates to charge people that would make the company earn money, or, you know, make sure that the company doesn't lose money. So from the perspective of the 30-year-old male, what are the values corresponding to the 2 events of surviving the year and not surviving the year? So here's where we create our random variable table. So this is going to be a small table in that there's only 2 scenarios. So the 2 scenarios are he lives or he dies. Scenarios. So the actual probability distribution table we'll create here. And their first question, as cryptic as it might be, is really asking for the two events of surviving and not surviving. So if he lives and if he dies, there's something that's going to happen with his money. Okay, so from his perspective, if he lives, what's up with his money? He paid $161, right? So if he lives, he loses $161. So losing $161, I would have a negative sign in front of that, just so I know it's a loss of money. If he dies, then his beneficiaries, I mean he's dead, but his beneficiaries will receive some money. Assuming that he let off $161 already, how much is his beneficiaries going to get? 100,000? Not quite 100,000. It's going to be 100,000, but we have to take into consideration the $161 that he paid off, right? So if we subtract this, what do we get? 99839. So if he dies, then his beneficiaries would receive $100,000, which in effect would have been just because of the $161 that he had already given to the company, it'd just be $99,839. So these are your random variables. So this random variable, it's a letter associated with a probability, right? A numerical value usually denoted by X, blah, blah, blah. So it's really a value that has an associated probability to it. So we have to associate a probability to it to complete our probability distribution table. So there is a 9.9986 probability that a randomly selected 30-year-old male lives through the year. This looks like it's a good probability to put somewhere. Which way is it going to go? The first slot or the second slot? First slot, because this is a probability that he's going to live. So 0.9986. Now, if that's 0.9986, what should the other one be? 1 minus that, right? So I think it's 0, wow, what is it? 0014? And if you add that, that should equal to 1 because this is a probability distribution table. Okay, we won't add that. We'll just assume that that's correct. So I don't know exactly how they would ask in the homework. I don't know exactly how would they ask A, but these are your random variables. These are your distributions associated with it. So this is your probability distribution table. Okay? All right, now let's see if we can address the other questions here. If a 30-year-old male purchases a policy, what is his expected value? Expected value. That's just the mean, right? And I'll write down the formula just to let you know that for a case like this, where there's only two scenarios, it's easy enough to think about using the formula because it's easy enough kind of math that it won't be that big of a deal. So I think it's x times p of x, right, with a sum? Yeah, okay. So what I can do to compute this is I probably want to make up another chart over here, extend this x times p of x. And I would multiply these two things, and then I would add them up. And then we would get the sum, whatever that is. So this isn't very much math, but already I don't want to do this. I just want to use a calculator. I know it. You do it and tell me. So what is the first one? Negative. Make sure there's a negative, or just put a negative after you. So 161 times 0.9968, or I'm sorry, 161 times 0.9986. 7746, and then 99839 times 0.0014. So if I were to add them, actually subtract them, right, because one of them is a minus, it looks like 160 is larger, so my final answer here is going to be a negative. What should this be? So his expected value is a loss of $21. That's not that bad from his point of view. From the insurance company's point of view, that's pretty good. And then if the insurance company has 50 or 100 of these clients who's paying, you know, overtime and going to be paying the company will be making $21 off each person over the long run. So this is good for the company. And an actuary would be looking at these numbers and trying to figure out a good balance. They usually don't want this to be zero because that means it's an even probability, and it may not be good for the company. So, but from the person's point of view, you should expect to be losing $21 a year. What? That's not too bad. It's for life insurance, yeah. Can the insurance company expect to make a profit from such policies? Yes, because over the long run, if they do this for a lot of people, then they would be expecting this. So I'd say yes. Yes, because in the long run, clients would be paying, and the company would make about $21 per client in the long run. All this is long run kind of behavior. It's hard to really, not too good to think about this client, you know, one client at a time, but it has to be seen from like hundreds and hundreds of clients that this $21 per client would make sense. All right. So now that we've seen how to do this by hand, I just want to quickly show how to do it using a calculator because it's fairly quick enough to see. I'm going to focus on the table because that's all we need from this problem. And let's start off by going to Stat and Edit. And I need two lists this time, so I'm going to clear out L1 and L2. So remember how to clear out the list, right? You go all the way up to the top, and then you hit Clear and Enter. Go up to the top, hit Clear, and Enter. If you accidentally hit Delete, if you go to the top and accidentally hit Delete, and all of a sudden you got L1, L3, L4, and then where's L2? Oh no. You can always insert it back. So to insert it, right above the DEL is INS, that's insert. So second function, insert, and then it's going to ask you, what do you want to insert here? I'm going to insert L2, so second function in 2, enter, and L2's back. So that's what happens when you deal with a missing list. All right, so for L1, I want to put in the random variables. And remember that the negative sign is different from a minus sign, so make sure you hit that negative sign correctly. So negative 161. And then the second number is 99839. So I want to go to my next list, and I want to make sure that it matches up. So that's 0.9986. and 0.0014. Okay? So the expected value is the same as the mean. So if I just find the mean, I can do this. But now I have two lists. So we're going to have to do the mean for two variables. So let's go to, I think you can just do one. All right, maybe, let me check first. Let's go to stat, calc. Let's try to do one var stats, because really we're just dealing with one variable here. One var stats. But this time I have two lists that I want to take into consideration. So I'm going to put L1, and then there's a comma here. This comma is what's going to separate the two lists. So comma, and then L2. And I press enter. What's missing? The standard deviation for the sample, the SX. So this one, you know to get the standard deviation, sigma, if you were asked for the standard deviation. This problem didn't ask us for a standard deviation. That's okay. But if you were asked for the find the standard deviation, then it's going to be this number over here. Okay. So we did a one var stats on L1 and L2. This, related to $21. I never really thought about putting this in a number line. Yeah, it's in dollars. It's standard deviation in dollars. Yeah, it is. Oh, because there is a big difference here. This is 100. The only two numbers that they come up here is negative $161 and then 99,000. So it kind of, in a way, makes sense, but it's still. Yeah, I don't know how the standard deviation would be described here. In any case, we got this one var stats by putting this into L1 and L2, one var stats L1, comma L2. And then that negative $21 that we got is the mean, and then the sigma, the standard deviation, is, this is in dollars, it's 3,739. Okay, we good with this example? All right, so this is just the beginning of our calculator work. What answer? Yeah, the standard deviation, it's because it's a standard deviation, it's the same units as the original data, which is in dollars. And I guess that's just a measure of spread between these two random variables, which, you know, it still doesn't make that much sense. But I think yeah, I think if we look at it from the point of view of gambling, it might make a little bit better sense. And let's not worry about it. Okay, good? All right, let's go back to our presentation, and this is our example. We have notes for this. So this is the first section, the introduction to random variables, discrete random variables at that. So now the next two sections will focus on a special type of discrete random variable or discrete probability distribution called the binomial distribution. So, let's go over to just to the definition here. A binomial probability distribution has 4 properties that it has to meet. A binomial distribution would be some experiment that we do over and over again, but for it to be a binomial distribution, we have to have this experiment happen a fixed number of trials, a fixed number of times. And there's different scenarios where this could come up, and we'll try to talk about a bunch of different scenarios. 2, the trials must be independent. Now, proving the trials independent is kind of a little tricky, but a lot of times we'll just assume that the trials are all independent. We did discuss independence last time when we talked about probabilities. But what they're saying here is that if we do a bunch of trials, what you do on the next trial is not going to be affected by what happened in the previous trial. Number 3, this is the word, this is the prefix by, where it comes from. Each trial must have outcomes classified into one of 2 categories. So, towards the end of the course, we'll talk about what we have. We'll talk about a multinomial experiment, and that's the difference here. Is there's more than 2 for the multinomial. For a binomial, there's only 2. Now, the 2 categories we'll refer to as success and failure. Now the word success is relative. It just means that's what we're looking for. Where in real life it might not seem to be a success, but that's how we'll call it. And then number 4, the probability of successes is going to be the same for each trial. Now, in the next page or 2, we'll talk about letters to represent this, and I'll put them here now since this is really an appropriate place to put it. The fixed number of trials will denote by n, and the probability for a success will denote by little p. So a scenario might be if you're taking a multiple choice test and all the problems have 4 questions or 4 choices, and then you just randomly guess. You don't even read the problem, you just randomly guess at this, and then there's 20 problems in your test. So that could be considered a binomial distribution. You have a fixed number of trials, you have 20 questions. Each trial is independent. You're randomly guessing. You're not going to base your answer for the current question based on the previous question. Or just randomly guessing. Each trial is classified into one of 2 categories. So there's 4 choices, but you either get it right or wrong. Right or wrong would be the 2 categories. And then the probability for success is the same for all trials. So for each problem, the probability of getting it right is 1/4. There's 4 questions, there's 1 right answer. So 1 out of 4. And the probability of getting incorrect is 3 out of 4. So the probability for each of those problems is 1/4 if you're randomly guessing. So that's one scenario, and then there's many other scenarios that we're going to run into. But I think taking multiple choice quizzes is a common first problem to look at, and it comes up a lot in your homework. So I introduced N and P as notation. There's more notation to introduce. They use S and F. We don't use it that much, but the probability for success, or the event of a success, they call S. The event of a failure, they call F. So again, not a big deal. The P is more important, and then now they introduce Q, which is the complement of P. Remember, these 2 are just one of 2 categories, so S or F is actually equal to the complement of S, which is, our notation is bar, right? S bar, or is it C? I think it's the bar. In any case, in some of these formulas, they'll be looking for P and Q, and P is the probability of success, and you just have to know what Q is. Q is the complement, or the 1 minus of that. Okay? Yeah, so there's going to be formulas where they'll ask for P and Q, or formula where you'll have to use P and Q. And we might as well get used to it, because this will come up later on, and there's going to be different P's and different Q's, like P hat, Q hat, P bar, Q bar. And whenever you see a P and a Q together, you can just think of that as complements. So P is P, and then Q is 1 minus P, 1 minus that. All right, more notation. A lot of this is stuff that we've talked about. N is the number of trials. Now, here X is the specific number that we're going to focus on, and so we'll use the word X. This will end up being your random variable. And then we talked about P and Q already, and P of X, P parentheses X, is the probability of getting exactly X successes. So the probability of getting X successes. So take a look at that 20-point problem, a 20-point quiz again, or 20 problem quiz or test. 1 of 4 multiple choice. So that N is equal to 20. P is equal to 1/4. That's a probability of getting the problem correct if this is a pure guess. And Q is going to be the complement of that, which is what? P 3/4. So if P is 1/4, Q is 3/4. And that's your complement. That's the probability of getting your problem wrong. Then I can ask, what is the probability that I get 10 correct, exactly 10 correct? This is the probability of getting 10 of 20 correct. So that's what PX means. That's the probability of getting exactly that many correct. Okay, and we'll find a way to compute this. This will be this will involve a difficult formula, but again, we'll rely on our calculators. Okay, let's move on. We got past the notation. I'm going to skip over this business, the hints. So methods for finding probabilities for a binomial distribution. Method number 1 is not the method that we're going to do. But if you remember the introduction of probability distributions, our probabilities are given with a formula or a table or a graph. And so this is the formula. And the formulas that come up in statistics are usually just stuff that's really difficult to comprehend. So you can look at the formula for a little while, but get past it. Don't dwell on it, and don't get sucked into this. But I should tell you a little bit about the formula. The PowerPoint will explain a little bit more about the formula later, but this exclamation point, n factorial, 5 factorial, for example, is a mathematical operation that takes the number of whatever n is and then multiplies down until you get to 1. And if you figure out what this product is, that's what 5 factorial is. Now, if n gets to be big, like 52 or something like that, then this is way too big to compute. And so we're going to need other ways to compute this binomial distribution formula. Okay, so one more look, and we'll go past it. Oh, by the way, 0 factorial is equal to 1. So this works for numbers that it's bigger than 1, and if you go to 0, then 0 factorial is equal to 1. That's just a special value. Again, not too important for what we need to do. Yes?
On the homework, there were questions that I had that formula, and when you type it in the calculator, when you do, give me an example or whatever, it'll show you like how to do it, and then when I tried to put the equation that they gave me on the calculator, it was like, one of the words was like E.
Yeah, so we'll talk about the E business, and that just means it's that's an exponent, a scientific notation, so you just have to move the decimal place over. Yeah. All right. So method 2 we definitely will not use, and that's using the table. They have tables in this book. I think tables used to be the way to go before they had technology, but again, I'll use technology that we don't ever have to look at another table again. So the third way is to use technology. Here our STATDISK is I don't know if anybody's messed around with it. Usually if it's a semester-long class, 17 weeks, we'll have time to go into STATDISK and take a look and see how that works. Has anybody take a look at STATDISK? No. It's a neat program. It makes a lot of the problems in your homework really easy to do and stuff. But since we don't get to take it into the test situation, we don't need to worry about it. Minitab is a popular statistical program that's used by researchers in the actual field, statistics field. So if you get into a field where you might need to do some statistics somewhere in the future, Minitab would be an option. There's another thing called SPSS that's used a lot also. Excel is another one that's going to be used a lot. It's easy and accessible, easily accessible for a lot of people. But for us, and for the sake of being able to do well on a test, we'll use our graphing calculator. Now this E that you're talking about, something like this, yeah, so when you see something like this, this is for 1, you take that decimal place and you move it this many times to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you're going to get 8 zeros before you actually start writing down your numbers. That's what that means, which means it's a really, really small number. Okay? All right, so we're going to use a calculator to figure out these probabilities, and so let's take a look at it. Here's an example, a slot machine. Whoops. So let's take a picture. Let me take a picture of this and put it into another file so I can annotate it. So slot machine, there's a 1 in 2,000 probability of winning the jackpot on any individual trial, although no one would seriously consider tricking the author. Suppose that a guest claims that she played the slot machine 5 times and hit the jackpot twice. Okay, so playing this machine 5 times would be our trials. There's 5 trials, right? And then whenever you pull down on the slot machine and then the slot goes, each of those trials would be independent from each other. Whatever happened in the previous spin has nothing to do with what's going to happen in the current spin. So their trials are independent. You either win or you lose. You win, and the probability of winning is constant. It's always 1 in 2,000. The probability of losing would be the complement of that, 199 over 2,000. So let's take a look at our scenario and identify the variables that we should identify, like our number of trials in this case is 5. Our probability of winning, our success, is 1 in 2,000. So our probability of losing, that would be Q, or failure, is 1999 out of 2,000. It's just a complement of P. So it says find the probability that you get exactly 2 jackpots in the trial. So what I want to do first of all is make a table out of this. I'll just make a table first, and we'll take a look at the different values, and then we'll talk about answering these questions with the table and then answering these questions individually with just the calculator command. So calculator, we need our calculator. To make a table out of this, let me go ahead and clear my L1 and L2. So this, by the way, would be the second way that I would suggest you do this. The first way to do this would be, I'll show you after we do this using a table. I think the idea of getting to know this with a table is a good practice, because you might be given the table and then you might be asked to figure out the probabilities based on the table. But for these binomial distributions, you should be able to do things without a table. Now let's do one with a table anyways. So if you play 5 times, how many times could you possibly win? What are our random variables in this case? Those two are the same question, by the way. No, not yet. I'm just talking about the random variables right now. What? Would it be 1 through 5? I would say close, but not quite. Could be 0 also. So you play 5 times, you could win 0 times. You can win once, twice, 3 times, or you could win all 5 times. Okay, so we want all those scenarios in our list 1. So I'm going to put in all those scenarios. So my random variables would be 0, 1, 2, 3, 4, 5. Now, for each of these number of wins, there's going to be an associated probability. There's probably going to be a high probability that you're going to win 0 times. And extremely low probability that you're going to win 5 times. So we should expect that. But what I'm going to do is I'm going to go up to L2. So cursor up to L2. So L2 is highlighted. And I'm going to construct a binomial distribution table for this probability distribution. So L2 is up. I don't have a parentheses down here, right? And I'm going to go to distributions, which is, let me clear the history here. So here, from here, second function in vars, which is really distributions. And I'm going to arrow down until I see binom PDF. Now, I get this far and I notice there's a binom PDF and binom CDF. You will be using both of these, and you have to know which one to use for which. In our scenario here, we're going to use PDF. So I'll press enter. Next, I'm going to use my n. So n is equal to 5. And then I'll say comma. And then I'll put my p. My P is 1 divided by 2,000. I can try to figure out what that is in my head, or I can just say 1 divided by 2,000, and then that should give me the same result. You can close the parentheses. The parentheses is right above the 9. And that's all we need for this. Press enter, it's going to give me a list of values. Now this kind of makes sense to what we talked about. There's a 99.75% chance that you're not going to win if you play 5 times. There's a 0.0025, that's less than 1%, a quarter of a percent, that you can win once if you play 5 times. And then winning twice, that's 0.05 zeros in a 2-5. So with this distribution table, with this probability distribution table, I can answer the questions that they have here. So find the probability that you win exactly 2 times in 5 trials. Let's get rid of that L3. 2 times in 5 trials. So to write this down in notation, probability that you win exactly 2 times is equal to, now I can write it like this, 0.25 e to the negative 6. If you forget to put e to the negative 6, then that's just 2.5, which is not a valid probability because it's bigger than 1. Or you can write this with a point 1, 2, 3, 4, 5, and then 2, 5. So that's a very small chance. So that's part A. Find the probability that you win exactly 2 times in 5 trials. Part B. Find the probability that you win at least 2 times. At least 2 times. So what does that mean? That means you can win twice, or you can win 3 times, or you can win 4 times, or you can win 5 times. So literally, you would say probability that you win 2 times, plus probability that you win 3 times, plus probability that you win, can I just put dot, dot, dot? I guess there's only one more here. Anyways, this is what it's saying. So I would want to add up all these probabilities here. So it's 2.5 e to the negative 6 plus 1.2 e to the negative 9 plus 3 e to the negative 13 plus 3 e to the negative 17, which is really, really small. It's really about the same thing as this anyways. So this is a very, very, very small probability. Does a guest claim of hitting 2 jackpots in 5 trials seem valid? No. So there must be something, this is the thing about the law, the small event rule or whatever it's called. If this were actually true, then there must be something else going on here. Okay? Any questions? All right, let me show you how to do this same problem a slightly different way. And without using the table, if all I care about is finding the probability of exactly two wins, in the calculator, I introduce the binomial PDF, and then I put in two numbers. I put in the n and the p. And whenever you do that in your calculator, what it's going to do is going to generate a list like it has here. But if I put the n and the p, and then I put one more number in there, that would be my x, then this is only going to give me one, this is going to give me exactly one probability. So again, this is your n, this is your p, and this is your x. So I would have to do that not on the list, but probably on the home screen. So let me take out my calculator again. And let me second function in mode and quit out of this, and let's clear everything so that I'm in my home screen. So, if you can remember where the binomial PDF is again, that's under second and vars, so that's distributions. And then scroll down to binomial PDF. Remember the PDF, not the CDF. So the PDF, and then I'll put in my n, comma, I'll put in my p, comma, and now I add in my last input, which is my 2. And then that's pretty much the same number as what I got in the table. So it's pretty much the same as that, right? A 1.49 that rounds off to 2.49 rounds off to 2.5, and e to the negative 6. So that's the same thing. So we went to the page where we saw PDF and CDF, and PDF stands for probability distribution. What do you think CDF stands for? No? Close? What? No? What? Say it again? Cumulative. Yes, exactly. Remember what cumulative was? We talked about the cumulative frequency, adding up all the previous ones, right? So the tricky part about this cumulative is cumulative from the bottom. So cumulative from the bottom, and by bottom I mean the lesser values. from 0 to 1 to 2 to 3 and stuff like that. This second problem that we have here, where it's asking us to find probability of at least, and I'm going to start using these greater than or greater than equal to symbols, at least 2 times. I would say x is bigger than or equal to 2. So what I want from this problem is I want to add up all these numbers from 2 all the way up to 5, right? Now, I can use this cumulative distribution problem, but the cumulative distribution starts from 0. So the binomial CDF starts from 0. But I want the rest of them. So what do I need to do to get the rest of them? So what I'm going to do is in my graphing calculator, I'm going to say binomial CDF n is equal to 5, P is equal to 1 over 2,000, and then I want to add up to cumulatively from 0 to 1, and I need to stop at 1. But what I'm going to get is these two things added up together. What I want is the rest of them. So after I get this answer, what do I need to do? I want to use the cumulative distribution function, the binomial CDF, but the cumulative distribution function starts from 0 and starts adding things up, right? So, but what I want is the sum of what happens from 2 all the way to 5. So when I punch this in the calculator, I'm going to get these two things added together. But I don't want those two things added together. I want the rest of them. So what special property do we have for the binomial, for any probability distribution? The whole thing adds up to 1, right? So if the whole thing adds up to 1, and I know a piece of it, but I don't want that piece, I want the rest of them, so I need to subtract this from 1. Does that make sense? That is the key to this problem where it says at least. So if it's at least, I need to look at the whole thing as one whole, and I need to subtract out the things that I don't want, and then I would have left whatever I want. That one's a little tricky. Okay, well, let me just punch in the calculator, and then we're overdue for a break. But if we go to second and vars again and look for the binomial CDF this time, and then I put in my 5, my 1 divided by 2,000. And this time, I'm not putting in 2, right? I'm putting in 1, so 1 less than that. and I need to subtract this from 1. Do you guys know how to subtract this from 1? 1 minus second and the subtract sign. The subtract sign or the, oh, this one, yeah, answer. Which is pretty much that 2.5 e to the 6th power that we had earlier, right? So it turned out to be very similar, the same thing. Okay, so let's take a break. When we come back, I'll show you the summary sheet that Frank has that has these calculator commands for the binom stuff. All right, let's take a 5-10 minutes